will stand here just between the lights. It's perfect. Okay, so welcome everybody to the talk on estimating the maximum possible earthquake magnitudes. So there are some bonus content for people who do speak Dutch, because I will be talking about the case of the Groningen province in the Netherlands. And this is joint work with Jan Berland, which was my PhD supervisor, André Kischko, who was a geophysicist from South Africa, and John Einmal from the University of Tilburg in the Netherlands. So to start, probably most of you have never heard about Groningen. So this is the Netherlands, and the top part, one of the top provinces of the Netherlands is Groningen. So indicated is in orange. And below Groningen there is one of the largest gas fields in the world, containing 2,800 billion cubic meters of gas. That was at the start, of course. Now there's already a lot taken out. So plus side, of course, if you have a gas field under one of your provinces, that's typically a large gold mine. So you get a lot of profits for this. But since they started in 1963, for the first 20 years, it was all going very well. But then in 1986, there was one downside which they didn't really take into account. That was that it induced earthquakes. And of course, these earthquakes are causing damage to the houses in the Groningen province. So on the map, all the black dots are earthquakes which are not natural but are induced because of gas extraction. So it's not only in Groningen province, also at the North Sea, for example, but we will focus on this area. And of course, if there are earthquakes in your area, houses getting damaged, this of course has multiple downsides. For example, also declining house prices. If you want to leave your area to move somewhere else, if your house is worth nothing, that's also a serious problem, of course. So the Dutch government did intervene. So the production is now lowered to 21 billion cubic meters of gas a year. It came from 54, so that's quite a substantial reduction. And for the future, they're going to reduce this to nothing anymore. So by 2030, it should be all stopped. So I'll briefly explain, because I'm a mathematician, not a geophysicist, what's going on there. So the blue, this is the plus content for people who do speak Dutch. So the blue line you see over here, this is the layer of sandstone which contains the natural gas. It's roughly above around 3 kilometers depth. And because it's very porous sandstone, whenever you extract the gas, the layer of sandstone subsidiates. And usually it compacts pretty evenly, pretty gradually. But at some points, which are the fault lines in the ground, certain pressure can build up, and at some point it can just break down massively and cause earthquakes. So that's the reason this is happening. And we are going to look at earthquake magnitudes. Why? Because there is a direct relationship between magnitudes and energy. So everybody probably knows the Richter scale, so that's the scale for the magnitudes. And it's basically a log scale depending on the energy expressed in megajoules. So there's always, whenever I'm going to talk about magnitudes, remember there's always a direct relationship, a one-to-one relationship with the earthquake, with the energy at the epicenter. And we're going to talk here about earthquakes which have magnitudes somewhere between 2 to 4, typically. For some people that might sound pretty low, but the problem is that in the Netherlands, this is the seismic energy at the epicenter. One problem is that it's very, very shallow, so only at 3 kilometer depth that these earthquakes occur. So that's very shallow. Plus the sandstone itself is very shaky, so it's not only the magnitude we need to take into account, but also the translation to what damage is gonna get. So, as I said in the title, we're gonna look for the maximum possible earthquake magnitude. So that's the maximum magnitude of an earthquake that can be generated by the geological structure of the area. That doesn't mean that in practice we will ever see this maximum possible, but it gives at least an idea. Okay. It gives at least an idea what the worst case scenario is. And it's important to note that this only depends on tectonic properties, not on the seismic activity itself. So even if you produce more gas or less gas, it's always this geological structure of the area that's going to determine this quantity. And we use it for worst case damage estimates. Of course, for engineering, when you build a new house, this is important to know. Also for damage assessment, it gives you worst case estimates of what you have to pay out. In this case, is the Dutch government together with the oil companies who get the gas out of the ground, we need to pay for this. And magnitude models, as we will see in a minute, is also a crucial element. So it's pretty important to determine this by denoted by capital TM. So of course, we're not the first one to try to estimate this. There's a whole literature in geophysics using parametric estimators. A famous model is the Gutenberg-Richter law. I will discuss this in the next slide a little bit more. And then more recently, also a lot of non-parametric estimators have already been developed to estimate this quantity. But I myself come from extreme value theory, so we will want to apply techniques from extreme value theory, mainly truncated Pareto and a truncated generalized Pareto distribution, to estimate this quantity itself. And it's also important to note that there is a lot of uncertainty on these estimates, so we want to use upper confidence bounds, so to not only give point estimates, but also to take into account that there is a lot of uncertainty in these estimates. So the Gutenberg-Richter distribution dates back already to 1956. And we start from an exponentially distributed random variable, which we call y. But y itself is not observed. We cannot see it. And y is unbounded, so we can get, in principle, an infinite amount of energy. This is, of course, not realistic in practice. So the Gutenberg-Richter law then says, okay, we observe these magnitudes m, but in distribution is the same as y, conditional on that y is between a lower bound, which we call small tm, and an upper bound, capital Tm. And the upper bound is exactly the maximum possible earthquake magnitude. This lower bound we don't really need to care too much about, but it's something larger than 0. In our case, it will be equal to 1.5. But it's important so that y itself is not observed, but conditional on y being between Tm and capital Tm, it has the same distribution as m, which we do observe. So that's a model in the Gutenberg-Richter connected with the exponential distribution. And it's not just some funny mathematicians who invented this model. No, it's actually coming from empirical evidence, and also there's a clear relationship with earthquake physics. So it's a mathematical model that has been proved, and in some cases also disproved, depending on the situation itself. So as I said, I come from extreme value theory. Well, extreme value theory, what do? We try to model extreme events. And what are extreme events? For example, very large insurance losses. Let's say, for example, a big fire in a big building. Financial losses, I don't have to give an example except for 2008. Everybody knows what I'm talking about. And especially natural catastrophes like floods, earthquakes. Originally, extreme value theory was used to model wave heights and so on in the Netherlands. What do we want to do? So we want to model these extreme events so we can compute large quantiles, return periods. So for example, how high should we build our dike such that once in 10,000 years it will only be breached, or hopefully not, of course. And endpoints of distributions as we do here. So of course, this is an R conference. In extreme value theory, a lot of people have already been making a lot of packages related to extreme value theory. The first one is Actuar, which is more for insurance purposes. EVD, EVER, F extremes, and QRM. And there is a grand task view called extreme value analysis, which gives an overview of these packages, so I only picked the main ones, of course. And last year, my promoter, Jan Berland, together with Hans-Erik Albrecher from University of Lausanne, and Jeff Teugels, also from the University of Leuven, wrote a book on reinsurance. So it's applying actuarial and statistical aspects of reinsurance. So it's applying extreme value theory, especially to the insurance context. But I, together with a colleague, made the package that complements the book, where we have a lot of estimators for extreme value theory, and also graphical methods such as QQ plots and so on to be used. And also extreme value theory estimators for censored and truncated data. So today I will talk about truncated data. People who were at USR last year, I talked about the methods for censored data. And this is the advantage that we can have both the estimators and then also compute risk measures such as a value at risk, fancy word for a big quantile, in one package. So everything I will tell today about the estimators is implemented in this package, which you can find on in CRAN, of course. So from extreme value theory, we start again from the same model. Now I will not have a small tm, but we start by saying that the magnitudes are in distribution equal to y, where we know that conditionally on y being smaller than this maximum magnitude. And based on the Gutenberg-Richter law, we expect that this that is y, sorry, has roughly an exponential distribution, so m has what we call a truncated exponential distribution. And before, we couldn't work with this, so what we did first is to move to the energy level. Remember the transformation, now it's written the opposite way. So if this is roughly a truncated exponential, you can compute this mathematically, then this would be roughly a truncated Pareto distribution. To believe me for this. And from extreme value theory, typically we always fit a Pareto distribution above a high threshold. So if we have a truncated Pareto distribution, we fit a truncated Pareto distribution to all the energy levels that are above a certain threshold t, for example 1.5, and we have to divide E by t, which we call the relative excess. So we fit a truncated Pareto distribution using maximum likelihood to these excesses, and then based on this model we can compute the first endpoint for the energy. So this then can be computed back to an endpoint for the magnitudes because there is this one-to-one relationship. That's quite important. But in practice, we have seen this works quite okay, but it's maybe better. Could be if we work directly on the magnitudes to get directly an estimate for the endpoint, and that's what we did in the paper last year. And we don't work with a truncated Pareto, but with the generalization, so the truncated generalized Pareto distribution. And then we can still work with the magnitudes. We don't look at the relative excesses, so not E over t, but here we do m minus t, but still above a high threshold, and then we get an estimate for the endpoint. So this is basically all the modeling that is behind this. If you want to know more details, you can read in our paper. But it's important to know that we can get an estimate for the endpoint through the energy, or we can work directly on the magnitudes. And these are the two extreme value theory estimates for the endpoint. So coming back to the example, in Groningen, so again the orange part here is Groningen, where the green, I don't know if you can see it properly, is roughly the area of the gas field. So there were 286 earthquakes between December 1986 and 31st of December 2016, just the endpoint of our study. And a lot of these magnitudes, since they were rounded, we're having a lot of ties, so we decided to add some uniform noise to have a little bit of variation in the data. And then in the end, we kept 250 smoothed magnitudes, which were larger than 1.5. So this choice of 1.5, you don't have to care too much, but this is a typical choice in literature to work with. And then we can compute estimates. I will first explain why we have what is on the x-axis. So on the x-axis, we plot k. And why is that the case? Well, we will use as a threshold the k plus 1 largest observation, and you can do this for every value of k. It's just we have to do extreme value theory above a certain threshold, and for each different value of this threshold, you will get a different estimate. So the first one, the truncated generalized Pareto distribution, is the one here in orange. So you see the estimates are around 3.8. How to choose the value of k, that would be a whole different presentation. And the truncated Pareto estimator is a little bit lower over here. And then I said, because we have to take into account the uncertainty, I also plotted 90% upper confidence bounds for this endpoint here and here. So they are roughly around 4. So that you see the estimates are 3.8, and they go up to 4, 4.1 if you take uncertainty into account. Of course, how can you compare this? Well, the maximum observed magnitude was 3.6, which happened in August 2012. Luckily, that hasn't been passed up to now. So this is actually what is the maximum. So if you would apply classical non-extreme value techniques, most of the time you will not end up too much above this maximum. And these classical techniques, one of them is a non-parametric one. That's where the NP stands for. And you see that this estimate is around 3.7. And this is the Kishko-Seleval estimator. That's a parametric one. And this estimator is roughly the same. And they both also have upper confidence bounds. Okay. So based on these techniques from extreme value theory and also the other ones, of course, we can compute these estimates. But mind that we also have to take the uncertainty into account. What's also important to know is that except for estimating this endpoint, some people can also say, but it's more interesting to look at, for example, the 95% quantile. This is also possible. I don't show it here, but this extreme value theory-based methods can be used for this. All the other estimators cannot be used for this. So the paper is available in Natural Hazard, and there's also an archive. And as I said, all the functions are implemented in the package. And there's also a Shiny app, which I will show in the last few minutes. If it works at least. And the Shiny app is also available on shinyapps.io. So here I plotted all the earthquake magnitudes above 1.5, so that's indicated over here. Otherwise, the map would be way too full over there. So you can, for example, select the time range, because that's one of the reasons we made this, because some people said, okay, how do you have to take the time into account? So with the slider below, you can then select which time range to look, and, for example, zoom into the Groningen province to see what's going on. And the black dot over here, that's the maximum observed magnitude of 3.6. And then, of course, there are a lot of graphs here. We'll run in a minute, showing the whole analysis. I will not discuss all of them, because it's the graphs that are available in the paper. But this shows, for example, how these magnitudes varied over time. So on the x-axis is the date, and on the y-axis the magnitudes. We'll skip all these, because it's too technical. And then you can see over here, this is the same plot as I showed before, with the estimates based on the truncated GPD and the truncated Pareto. And of course, if you shift the time slider to different periods, these maps will update. These graphs will update as well, so you can see the influence of choosing a different time period, for example. And then below, I gave the values based on a certain value of k that we also used in the paper, and together with the upper confidence bound to give an idea about how these endpoints are calculated. And all these methods are explained in the paper as well. It's too much to cover now. But you see that we have estimates around 3.77 using a truncated GPD, and with the uncertainty it's up to 4.04, a little bit higher. So we'll move back to the presentation. So thank you for the attention. If there are any questions, I would gladly answer them, of course.
So do we have any questions? Put any hands up? Okay, I'll come down to you now. Whoops.
So once you have those graphs that you showed us, how do you go about choosing a value for k? I mean, I see that like on the right end, the graph is kind of smooth, so it doesn't matter that much. But if you wanted a precise measurement, how would you do it?
Can I get the screen back? Okay. Sorry. So we'll just point it here. So on the left side, there is a lot of variability. That's the reason is because if k is small, that means that this value is pretty large, so you're not using enough data. So you kind of stay away from that area. And indeed, if you move to the right, especially for these estimates, it's not changing too much anymore. There are several tools in extreme value theory to give you a guidance. Would be too much to discuss them here. But in the paper, we used a value around here. Because indeed we have some kind of stable area over there. But there is no, let's say, automatic way of doing this, unfortunately. But that's one of the problems with extreme value theory that still hasn't been solved. But indeed here, if you choose a value around here, or even here, this would all make perfect sense. But as I said, it's also important to take the uncertainty into account in the first place, of course.
We might have time for one short question if anybody's got another short one. No? Okay, so we'll just thank our speaker there, give him a round of applause, and we'll just get ready now for the next speaker.